faithfully conveying value, interpreting great books from around the world.
Hello, this is Sally's Book Talk. Today's book for you is called Aurora, subtitled Exploring the Wonders of Light in Polar Civilizations and Natural Science.
Angela Chang's song Aurora made the mysterious northern lights a longing in many hearts. The song title Auroral transliterates Aurora, the Roman goddess of dawn. Astronomer Galileo named the lights after Aurora. In freezing polar nights, unpredictable colorful bursts appear. That's the aurora. It's considered one of nature's most beautiful wonders. Simply put, it's when charged particles from the sun collide with Earth's atmosphere. So, what does aurora look like? Even seeing it firsthand, words often fail to capture it. Against pitch black skies, auroras explode in dazzling colors like burning paper, outshining all stars.
Witnesses say the strangest part is not knowing how you'll react until you see it.
A spectacular aurora display feels like receiving a gift. Author Melanie Windridge, PhD in plasma physics from Imperial College London, is also a polar explorer who visited aurora hotspots like Sweden and Canada, examining auroras through mythology, science, and culture. All right, I'll now explore the book's core ideas through 3 questions. First, how did historical cultures perceive auroras? Second,
How are auroras actually formed?
third, where are the prime aurora viewing locations? Let's begin with the first question. How did people historically view auroras? In 10,000-year-old French caves, early humans drew curtain-shaped auroras on ceilings with red clay. And this is considered humanity's earliest aurora record. The earliest written descriptions date back to 2000 BC. In Genesis, auroras appear as divine light representing God. China's Records of the Grand Historian describes the Yellow Emperor's mother seeing a grand hall circling the North Star. This grand hall refers to auroras. Legend says she saw auroras near the Big Dipper, then conceived the emperor. Whether in China or West Asia, the birthplace of the Bible, both are in temperate zones where auroras are extremely rare sights. So people back then saw the aurora's appearance as some kind of omen or a warning that something big was about to happen. It's said that before Caesar's assassination in 44 BC and before the outbreak of the American Civil War in 1860, rare red auroras appeared over Italy and the US, while in the Arctic Circle, auroras are quite common. Although auroras have long been part of local life, people still hold them in awe. The author once met a Norwegian reindeer herder who said he was terrified of auroras as a kid because his parents warned that if you angered the aurora, it would swoop down and drag you away.
In these herders' minds, the aurora is like a natural nanny, urging kids to rush home before dark.
The legends about auroras among people here are even richer and more fascinating. For example, in North America, the Inuit people living in polar regions believe auroras are the souls of the dead dancing, deceased folks holding banquets in heaven, and they even kick walrus skulls around like soccer balls. The auroras people see are the shadows of deceased loved ones.
The legends about auroras among Northern Europeans are even more magical.
Bens believe an Arctic fox runs wildly, sparking fire with its tail on the snow, thus creating the aurora. Therefore, in Finnish, the word for aurora means foxfire. Norwegians think auroras are tied to schools of fish in the sea. Groups of silvery flying fish project their shimmering scales into the sky, forming the aurora. In Danish folklore, the aurora is the reflection of a swan trapped in an ice cave in the sky. The swan, flapping its wings hard, creates the dazzling aurora. I wonder if you've noticed that all these legends unanimously give the aurora a soul. Even the author himself said that when he witnessed the aurora firsthand, he naturally felt the spirituality mentioned in those ancient beliefs. Even now that people know how auroras form, this feeling still lingers. However, what exactly is the aurora? How does it come about? Ancient people understood auroras purely through imagination and legends. Some even speculated auroras might be otherworldly beings with powerful forces, leaving unique symbols on Earth, but humans haven't found a way to decipher them yet. Until the first 2 decades of the 17th century, multiple large-scale aurora outbreaks occurred. Not only Nordic countries, but southern European nations like France, Germany, and Italy could witness the dazzling auroras. At this point, scientists like astronomers Kepler and Galileo began exploring the scientific causes of auroras. Galileo deduced that auroras might be related to both the sun and Earth's atmosphere. Galileo believed Earth was enveloped in a layer of vapor, and this vapor, reflecting sunlight, created the aurora. Research by other contemporary scientists also supported Galileo's view. For example, French scientist Jean-Jacques d'Orton de Mayerne observed that auroras occurred most frequently during intense sunspot activity. By the 18th century, intense auroras reappeared across much of Europe, leading to new theories about their origin. The renowned British scientist Edmund Halley speculated auroras were connected to magnetic substances. He thought magnetism could penetrate all matter, and when passing through the atmosphere, it would cause friction, creating the magnificent lights. Others later confirmed Halley's view, since compasses were heavily disrupted during auroras, losing directional accuracy. In the 19th century, Europeans grew increasingly fanatical about polar exploration, racing to the Arctic, partly for geographical discovery and research, partly for territory and resources, regardless of motives. During this period, scientists flocked to the Arctic region, making auroras a key research focus. Although they hadn't pinpointed the exact cause, they determined two things: the approximate altitude of auroras and their geographical visibility range. With their constant movement and graceful forms, auroras give the illusion of being within reach. But through triangulation, scientists discovered auroras actually occur hundreds of kilometers above Earth. So what exactly is triangulation? Imagine a distant tower. Its base and top form a right triangle. When you look at the top, there's an elevation angle. As you walk closer, the triangle changes, altering your viewing angle. You don't need to climb the tower. Just measure your movement distance and the different elevation angles, then use math to calculate its height. Triangulation is widely applied in the scientific community. For example, using this method, scientists roughly measured Mount Everest's height as 8,840 meters before ever climbing it. Only a few meters off from today's precise measurement of 8,844.4.3 meters. Beyond measuring aurora heights, scientists also discovered it's not true that the further north you go, the higher the chances of seeing auroras. Auroras occur in a ring-shaped region called the auroral oval. This oval roughly circles the Arctic. Moving further north toward the pole actually reduces visibility. By the early 20th century, Norwegian explorers reached Antarctica, finding not just adorable penguins, but equally stunning southern lights. Southern lights resemble northern lights in form, with symmetric viewing locations. They appear like twin phenomena above Earth's poles. All right, that concludes the first question. How did people historically understand auroras? Humans recognized auroras since ancient times, creating beautiful legends about them. Modern polar exploration gave deeper scientific understanding, but the mystery of aurora formation wasn't solved until the 20th century. Now, let's explore the second question. How are auroras actually formed? Norwegian physicist Christian Birkeland pioneered aurora theory, a polar explorer who established multiple observation stations. By the early 1900s, physics had advanced to microscopic levels. Atoms were understood to contain electrons and protons, particles carrying electrical charge, since electric fields create magnetism, and magnetism affects charged particles. This is electromagnetic induction. In 1908, Birkeland proposed solar-charged particles reach Earth, funneled by its magnetic field to the poles, creating auroras.
To prove this, Birkeland designed an experiment,
magnetizing a metal sphere in vacuum to simulate Earth.
This small metal sphere was coated with fluorescent brass that glows when struck by electrons. When Birkeland shot cathode rays, electron streams, at this simulated Earth, he observed artificial auroras forming ring patterns near both magnetic poles, remarkably similar to real auroras. Birkeland's theory is now mainstream science's explanation for auroras, but it wasn't immediately accepted back then. The reason? Earth's dense atmosphere prevents direct observation of solar-charged particles from the ground. Only half a century later, in the 1960s, when spacecraft left Earth and actually observed solar particles in space, was Birkeland's theory widely accepted. Actually, auroras form through the interplay of solar wind, Earth's magnetic field, and atmosphere. The primary instigator is the sun, a massive plasma sphere undergoing constant nuclear fusion. So what is plasma? Unlike Earth's solid, liquid, or gas states, plasma forms under extreme heat, pressure, or magnetic fields. Lightning, for example, occurs when gases become plasma. While rare on Earth, plasma dominates the universe. A staggering 99.99% of cosmic matter exists as plasma. Its high-energy electrons store immense energy, constantly released as radiation, like the sun's light and heat. But plasma's instability causes the sun to eject charged particles at high speeds, creating solar wind. Solar wind's speed is unimaginable. Earth's strongest hurricanes reach 30+ meters per second, while solar wind blasts at 300 to 400 kilometers per second, over 10,000 times faster. You can imagine the impact when such high-speed particles collide with Earth. Thankfully, Earth's thick atmosphere, extending 100 kilometers high, shields us from solar wind. We call the point 100 kilometers above ground the Kármán line, proposed by Hungarian-American physicist Theodor von Kármán and named after him. This line is considered Earth's boundary with space, where satellites and spacecraft operate. For example, the International Space Station orbits about 400 kilometers up. But above the Kármán line, Earth's atmosphere doesn't vanish, it just gets thinner. And Earth's atmosphere extends up to 3,000 kilometers. Above the Kármán line, temperatures reach hundreds or thousands of degrees, and strong magnetic fields excite air into high-energy plasma. Earth's magnetic field reaches even farther, up to 30,000 kilometers, outpacing the atmosphere. When solar wind particles approach Earth, they're drawn toward the magnetic poles, colliding with the atmosphere. Most collide with plasma-state air particles above the Kármán line, releasing light energy. That's the aurora. After confirming aurora's cause, research continues advancing. First, we've pinpointed aurora's exact altitude, mainly 100 to 250 kilometers high. Solar particles guided by Earth's field approach the poles. Rising air density increases collision chances with atmospheric ions. Collisions peak between 100 to 250 kilometers altitude. That's why the most spectacular auroras occur there. Typically, most solar particles can't penetrate below 100 kilometers, the Kármán line. Scientists also found aurora intensity and visibility relate to solar wind strength. Earth's magnetic field and atmosphere stay relatively stable, but solar activity changes cyclically. So aurora strength mainly depends on solar activity levels. Solar activity follows an 11-year cycle. Its calm, low-activity phase is solar minimum. During solar minimum, solar wind blows gently, causing milder particle-at-atmosphere collisions. During solar minimum, the auroral oval narrows to a thin circle, with only a few polar regions seeing faint auroras. Conversely, when the sun becomes violent and hyperactive, that's solar maximum. At this stage, the sun's magnetic field severely distorts, even reversing polarity, causing massive explosions in its atmosphere. People on Earth witness intense solar flares. These flares eject billions of tons of coronal mass, material from the sun's outer atmosphere, into space, forming colossal solar storms. When solar storms reach Earth, they violently react with our magnetic field and atmosphere, creating brilliant auroras. Though occurring every 11 years, each solar cycle's intensity varies. Scientists classify solar wind using the KP index from 1, weakest, to 9, strongest. Every 500 years, an exceptionally massive solar outburst occurs. For instance, 1859 saw the strongest solar storm in centuries, reaching KP9. Back then, vivid auroras dazzled Europe and America. Even tropical Caribbean nations saw them, revealing aurora's colorful diversity. Different colors emerge from solar particles interacting with various atmospheric particles. Most auroras appear green, caused by solar electrons colliding with plasma-state oxygen atoms. Green auroras typically occurred near the Kármán line. High air density, proximity to ground, and human eyes' strong green sensitivity in darkness make them most common. Red auroras are rarer, forming above 200 kilometers and requiring stronger solar wind. They're typically visible only during solar storms. Oxygen atoms emit red light only under extremely high energy impacts. Beyond these, blue, purple, and pink auroras are exceptionally rare. These colors result from solar wind striking nitrogen atoms. Human eyes poorly detect these wavelengths in darkness, and nitrogen emits weaker light, often obscured by green auroras. Since auroras are typically nocturnal, they're called nighttime auroras. Actually, daytime auroras exist too. Besides charged particles, solar wind contains neutral particles, like neutrons, uncharged and unaffected by Earth's magnetic field. So they travel straight toward Earth's atmosphere, like sunlight, exciting atmospheric particles to glow. Daytime auroras are usually faint and masked by intense sunlight. They're nearly invisible to naked eyes, typically detectable only with specialized instruments. All right, that concludes this part. We've now covered the book's second question, how auroras form. Charged solar particles, guided by Earth's magnetic field, collide with atmospheric particles above the poles, releasing light to create auroras. Auroras typically occur 100 to 200 kilometers high. Intense solar activity often produces stronger auroras. Different colors result from varying solar wind strengths interacting with oxygen, nitrogen, and other particles at different altitudes. Since auroras are so captivating, where can we actually see them? That brings us to the third question. Many want to see auroras without traveling abroad. Can Mohe, China's northernmost town, offer that? Mohe's Arctic village sits at 53 degrees, 33 minutes north, truly China's closest point to the North Pole. Some tour companies promote aurora sightings as a Mohe travel gimmick. But here's the reality. Even most locals haven't seen them. Spotting one during a short stay would be like winning the lottery. Though Mohe is China's northern tip, it's far from the regular auroral oval. As mentioned earlier, the auroral oval typically circles near the Arctic, but centered on the magnetic North Pole, not the geographic one. The magnetic North Pole, while near the Arctic, doesn't coincide with it and constantly shifts position. For example, in 1996, it was located at 79.3 degrees north, 71.5 degrees west, in the strait between Canada and Greenland. And with the magnetic pole in the western hemisphere, the auroral oval tilts westward. Even during solar maximum, when the oval expands south, Mohe has far lower odds than western hemisphere locations at similar latitudes like London or Berlin.
Despite this, Mohe remains China's most likely spot to see the aurora.
Only when solar activity hits KP9 does the auroral oval's edge reach Mohe, allowing naked eye sightings. Other times, only sensitive instruments can detect extremely faint auroras in Mohe. For truly spectacular auroras, head to high-latitude Western Hemisphere locations like northern Sweden or Norway, ideal year-round viewing spots. With luck, you might witness an aurora explosion. Take Kiruna in northern Sweden, not just a skiing mecca, but also a premier aurora destination. Compared to Kiruna, Norway's Finnmark County offers wilder, more pristine environments. Minimal light pollution makes auroras appear brighter and clearer here. You can stay in forest cabins and ride snowmobiles to mountain peaks for aurora viewing. In Finnmark, you'll not only see auroras but also experience the indigenous Sami culture. The ancient Sami people are also called Laplanders. Having inhabited the Arctic for millennia, the Sami host an annual dog sled race, the world's northernmost. The 1,000-kilometer course crosses Norway, Finland, and Russia. All of Iceland lies within the auroral zone. With sparse population and active volcanoes, many tourists hike and camp in uninhabited grasslands. Budens in southeast Iceland, for instance, is a renowned camping area. Crystal clear air reveals ice caps and volcanic remnants by day, while campsites offer nighttime aurora views. Svalbard Archipelago in the Arctic Ocean is another prime aurora location. Discovered in the 16th century as a European whaling hub, Svalbard now hosts research stations, including China's Yellow River Station. Given Svalbard's high latitude and position inside the auroral oval, northern lights usually appear in the southern sky. Here you'll witness not just spectacular nighttime auroras, but also daytime ones. Near Longyearbyen, a specialized aurora station uses custom instruments to observe dark red daytime auroras in the upper atmosphere. At the other end of Earth, the Antarctic also has a powerful auroral oval. Whether observing in Arctic or Antarctic, winter is prime aurora time due to extended polar nights. Longer darkness means better viewing. Antarctic winters bring brutal cold and harsh conditions, making deep continent aurora viewing extremely challenging. However, near Antarctic regions like New Zealand can still offer aurora sightings under right conditions. Even at ideal locations, catching auroras requires luck. Since auroras form over 100 kilometers high, thick clouds or precipitation can block them completely. Plus, while some areas see auroras year-round, they only become truly brilliant and spectacular during intense solar activity. Institutions like NOAA's Space Weather Prediction Center forecast auroral zones and intensity based on solar activity. Monitoring their 1 to 3 month forecasts can significantly boost your aurora chasing success. Here's a secret weapon: night vision goggles. They amplify faint light, transforming barely visible auroras into vivid, dazzling displays. While we focused on ground viewing, aerial perspectives offer clearer, almost firework-like spectacles. So on transarctic flights, glance outside. You might save that dedicated Nordic aurora trip. From space, auroras reveal their true form, no longer mere pillars or rainbows. Instead, they crown Earth's poles like a royal diadem. We've now covered the book's third question: where to see auroras. A ring-shaped auroral oval circles the magnetic poles, the prime viewing zone. In the northern hemisphere, top locations include northern Norway and Sweden, Iceland, and Svalbard. While auroras are beautiful and romantic, everything has two sides. Their most spectacular displays coincide with solar maximum, when intense solar storms can disrupt Earth's technology. First, it affects man-made satellites operating in space. Massive charged particles in solar wind bombard components like solar panels, causing performance degradation or failure, especially during solar flares when high-energy protons erupt. Protons cause far more damage than electrons due to their greater mass. For example, the 2003 Halloween solar storm lasted days. Intense auroras appeared over the Arctic, visible as far south as Florida, Texas, and Italy, but over 50 satellites malfunctioned, and Japan's Earth observation satellite number 2 was destroyed, crashing into the atmosphere. Secondly, intense solar wind disrupts Earth's magnetic field, affecting communication and power systems. As mentioned, auroras occur in the ionosphere, which reflects radio waves, enabling long-distance wireless communication. Strong solar wind disrupts the ionosphere, causing communication interference or blackouts that trigger serious accidents. For instance, aircraft communication failure could cause catastrophic crashes. Solar wind also triggers drastic changes in Earth's magnetic field. Through electromagnetic induction, these magnetic shifts induce massive currents in power lines, potentially frying equipment and causing local blackouts.
In 1989, intense solar activity blacked out 90% of Quebec, Canada. The aforementioned 2003 solar storm caused power failures and blackouts across the US, South Africa, and other nations. Thirdly, solar wind's charged particles impact human health. These particles emit radiation. Astronaut suits provide protection for this reason. Earth's thick atmosphere blocks most particles, but at polar altitudes, they still pose health risks. However, occasional long-haul polar flights during solar storms won't significantly affect health, but long-haul flight crews face significant health threats. NASA research shows high-altitude crews receive more radiation than nuclear plant workers, with higher risks of skin cancer, breast cancer, and other malignancies. That concludes the main content of Aurora. After the solar system formed, Earth developed its magnetic field and atmosphere, creating auroras over 4 billion years ago. Humans have understood aurora formation for just over a century, with many mysteries still unsolved. For example, why is the auroral oval ring-shaped? How exactly does it connect to Earth's internal magnetic structure? And why do people hear strange, hissing or crackling sounds from the ground during auroras? These mysteries require further scientific exploration. All right, that wraps up our exploration of Aurora. Find show notes below the audio. See you next time.